Okay. So last question. Determine the order of the active filter. So again, I believe the way to determine the order of active filters is to count the number of frequency dependent devices. What does frequency dependent devices mean? It just means the number of capacitors or inductors. Okay, because think about it. For impedance of capacitors, the formula is 1 over j omega c. See, it depends on your frequency omega. Then what about inductors? It's j omega l. See, again, it's dependent on your frequency. But what about, for example, resistors? No, it doesn't depend on omega. Do you see omega? No, omega doesn't show up. So you count the number of capacitors or inductors present in the active filter, then that will determine your order. So in this case, I think the order is only 1 because you only see this capacitor. That's all. So the order is, so since the order is 1, this implies that it is a first order. If there are 2 devices, then it'll be second order, and so on. Okay, so it's first order. Next, using symbolic equations, determine the frequency response H of the active filter. Okay. So the frequency response, remember the formula is given by V out over V in. So that's our objective. So let's see if we can get V out over V in. Again, you see an op-amp, right? The no-brainer thing to write down to retrieve at least some marks will be to show V plus equal to V minus, I plus equal to I minus equals to 0, and KCL wherever you can. So can we simplify anything right off the bat? Yes, we can. So look at the plus terminal. It's connected to the ground, meaning to say this is 0. So we know V plus equals 0. And we know for a fact that V plus equal to V minus. So that means this is equal to V minus. So that means up here, V minus is also equal to 0. And notice that this whole thing is a node, okay? This whole thing is a node. Okay, I'm just gonna make the node go up until here, okay? So that is the node that is connected to the V minus. So this is 0. And okay. So now what do? We just take KCL wherever we can. Doesn't make sense to do KCL over here, right? Because we established that I plus is equal to 0. So let's do a KCL at this node, right? So assume the directions. So going in like this and coming out like this. Now the coming out is a bit difficult to see, but we can lump this, we can lump that arrangement in this box as a single impedance, right? Let's call this ZA. Okay. So let us leave ZA to be for now, but we know that it goes through ZA also, right? See, if you think about it, it comes out from this node and passes out through ZA into the output terminal. Okay. So KCL means current going in equals to current going out. So who's the current going in? First, we have this current going in. So remember, currents, we had to express them as delta V over R, where delta V is V start minus V n divided by the impedance. Okay, so for example, the current going in, this one, we start from here, we end at here. Okay, so V start minus V n is, we start at V in, we end at this, which is V minus. So, so KCL at minus shows that current going in is V in minus V minus divided by R1. And then, so now the current going out, please don't be confused. This current going out is here, okay, going through ZA and coming out at V out. So where's the V start, where's the V end? It starts at this V minus node. See, it starts at this V minus node, and then it ends at this V out. So it's V minus minus V out, V minus V out, divided by the impedance ZA. Okay? So we can begin to simplify things. What do I mean? See, remember we identified that V minus is equal to V out from the ground terminal. Yeah, so we can replace every V minus with V out to simplify our working. So this drops. Okay, so from here, what we can achieve is, oh, I don't have enough space, sorry. So if I continue up here, what we can achieve is V in divided by R1 is equal to negative V out divided by ZA. So remember our objective is to find V out over V in, correct? So I'm going to throw this down here, and then I'm going to move ZA up here. So I get V out over V in ZA divided by R1, and I'm going to throw this negative to this side. Okay, so we're not done yet because ZA is something we created. Now we had to find ZA ourselves. So let us go ahead and find ZA. Now let us focus on ZA. Inside ZA, what do we have? We have this resistor R3 connect. Oh dear. Okay, and let me just clear this again. Okay, so what do we have? Inside ZA, we have this resistor R3 connected in series with C1. Okay, we can establish that. So to find their total impedance, we add them up together. And then what else? We have R2 parallel to this branch of R3 and C1. Okay, so we had to add them up using the parallel formula. So let us go ahead and find 1 over ZA. So 1 over ZA, let me just do this in black. 1 over ZA is equal to 1 over R2 plus 1 over this R3 plus the impedance of the capacitor. R3 plus 1 over J omega C1. Okay, I hope you can see that. This, oh, sorry. This comes from the fact that R3 and the capacitor are in series, while this whole thing comes from the fact that R2 is parallel to the branch containing R3 and the capacitor. Okay, so now let us solve for ZA. How can we go about doing this? Okay, let's just find ZA as a very horrible thing. So what am I gonna do? I'm gonna take this entire thing, throw it down here. Take this entire thing, throw it to the numerator. So if we solve for ZA, what do we have? We get this. Okay, this behemoth. Okay, now let us get back this relation. So we have found that the frequency response is given by this. So now let us substitute our ZA, our beautiful ZA, meaning this, into the equation of the frequency response. So our frequency response, V out over V in, is given by, so I can say this is the same as negative 1 over R1 multiplied by ZA, correct? I just bring this ZA down here. That's why it's like this. Then I'm going to replace this ZA with this expression. Okay, so I'm going to straight away replace it, erase this, and then paste it here. Okay. And yeah, actually, you can just leave it like that. But if you want to be anal about it, you can multiply this into here and here. So I'm just going to go ahead and do that for you. So negative 1 over R1 divided by R2 plus R1 divided by R3 plus 1 over J omega C1. I notice a lot of students are very tempted to simplify something like this. They're always, I don't know why people are naturally afraid of seeing big fractions. No, fractions within fractions. People are so afraid of seeing this kind of thing, but just leave it be. It doesn't matter. Yeah. So now moving on to question C, using symbolic equation, determine the gain at low frequencies and the gain at high frequencies. So this means take the limit of your gain as omega approaches 0. So limit as omega approaches 0. Okay, so you just take this thing. Okay, now you can drop away this negative sign by taking a modulus because we're not interested in the sign. The sign merely tells us whether it's inverted or not. In this case, it is inverted because it's negative, but that's not of interest to us. What matters is the gain, is the amplification effect. Yeah. So now we can focus on letting omega tend to 0. So focus on this character because he has 0. So we let this become 0. 1 over 0 means this whole thing becomes infinity. Okay, so this goes to infinity. Now, look at this. Something plus infinity should give me infinity. So this entire thing is infinity. Now, look at this. Something divided by infinity means I get 0. So actually, this whole term drops away to 0. At the end of the day, what do I have? I have 1 over R1 over R2. So that means my result is R2 over R1 because it's the reciprocal of this, right? This whole thing has already dropped away, leaving behind 1 over this. So I take the reciprocal of R1 over R2, getting this. Okay. Now let's take the ooh, now let's take the limit. So this is the answer to C part 1. Now C part 2. Omega approaches infinity of the same gain. Again, we can drop away the negative using the modulus operator. Drop this away. Now, focus on this. Make this go to infinity. So this 1 over infinity means this thing should just drop away. This goes to 0. 1 over infinity is just 0. Meaning to say, we only left behind this and everything else. So just copy them down. So what you have at the end of the day is 1 over R1 over R2 plus 1, sorry, R1 over R3. Okay, so that should be it. Uh, the gain at high frequencies, this is the gain at high frequencies, so this is C part 2. The cutoff frequency, simply look at the denominator of the frequency response. I don't know what that means. I actually legitimately don't know what that means. But okay, to solve for the cutoff frequency, let's try to use the tip that I gave in tutorials, which is to say we need to solve the magnitude of h uh, equated to h naught divided by root 2. Now, we have to find who is the h naught. That means we need to compare, of the two of these, who is greater. Now, this is not an easy test to do, but let me just try and see how we can go about doing this. Okay, so this is not easy. This R1 and R1, let's try to divide them. I mean, let's try to factorize it out. Okay. Um, Now what I'm gonna do is simplify this into a single fraction. So cross multiply. Okay. Look at what I'm gonna do, okay? I'm gonna pull this R1 to the outside of this fraction. If I do so, it will look like this. See, I'm gonna pull out that 1 over R1, and then the rest of it, I just copy down. Okay. Now what I'm gonna do is I have to compare against this. Okay, let me think, because I don't have any solutions, so I'm thinking this on the spot. Did you tell me what R3 and R2 is? No, there's no values at all. This how am I supposed to make a numerical comparison? This is not easy. Okay, so what I'm thinking is, because they tell me, oh, reciprocal of this term. Reciprocal, so just flip it around. Okay. Flip it around means 1 over R1 multiplied by R2 over R3 plus R2. Now I had to compare against this. Okay, let me just compare. If I pull this away, see, I'm trying to compare this. So this thing is the same. Ah, okay, idea. Okay, you see, look, these two are the same, right? So we don't need this to compare. Well, how are we gonna compare? Who is greater? Number one or number two, right? We don't know. Okay, wait. Sorry. Let's not call it number one, number two. This is the low frequency limit. So the low frequency limit, I'm just gonna call it L. And this is the high frequency limit. I'm gonna call it H. So who is the larger value? L or H? The answer is, sorry, who is the higher limit? The answer is L, right? Because let's just plug in some numbers. Let's say, example, R2 is equal to 2, R3 is equal to 1. So if you sub it in, right? So you see, let's look at the high frequency limit. It's 2 over 1 plus 2. This is 2 over 3. Whereas R2 is just 2. Who is larger? 2 over 3 or 2? 2 is larger. That means the low frequency limit is the larger value. Okay? That's why I re-manipulate it. Okay? You see, at first it was in a very ugly form, right? But then I had to re-manipulate it so that I can compare it fairly with this value here, right? I make it similar by taking out this 1 over R1 so that I can compare it against, because this is just the same number multiplied by another number. So to determine the larger of the two, I just need to compare these two. Okay? And then if you think about it generally, right? This is some number divided by itself plus another number. So you see, the numerator is smaller than the denominator. When the denominator is larger than the numerator, then you know this is like a less than one value. Yeah, it's less than one. It's a value that is, it's a number. This whole number is less than one. Yeah. So that's my point I'm trying to make. Okay, so we know that. So now that we identified that this is the larger value, we know that this is the H naught. Okay. Now that we know that this is H naught, we can sub it into this expression. Okay, and we have to achieve our gain again. This is our gain. Okay, our gain is this thing, right? So it says to take the modulus of this. Modulus of this means I can drop away this. And then we also know that we can split the modulus between the numerator and the denominator, right? But then the numerator shows modulus of 1, which is just 1. So I can drop that away. Now, our job here is to make the numerator look like this numerator on the right-hand side. So what do? We need to just multiply by this numerator. So how do you change 1 into this? You can multiply it by this. So what I mean, just multiply it by R2 over R1. And then the numerator, you can do multiply by R2 over R1. And this too, R2 over R1. Yeah. So 1 times this is just itself. And then look at this. The beauty is that this can cancel with this perfectly. This can cancel with this perfectly. So altogether, that becomes 1. This cancels this cancels this becomes 1 plus. Now look at this. This cancels with this, leaving behind R2 over R3 plus 1 over J omega C1. Okay. Now that the numerators are equal, we can equate the denominators. I'm actually very unsure about this. I feel there's something gonna be not easy about taking this modulus. Okay, something gonna be not easy about taking this modulus. Because look at this. Wow, this is not easy. Let me think about it. Is it because you cannot split this modulus like this. You can't. I'm trying to avoid. Okay, you know what? I'm just gonna do as I can. So I'm sorry if I'm wasting your time, but I have no choice. I gotta do this, work it out as I can. Sorry. So so what I'm trying to do is gonna get rid of this. To get rid of this, I multiply j omega c here and j omega c to this top. It's not something usually I would do, but the circumstances call for it. Now what I'm gonna do is express this as a single fraction. So this time this. At the top, I'm gonna group the imaginary terms together. Now, what I'm gonna do is I'm gonna split the modulus between the numerator and the denominator. Okay, then you see this is modulus of a complex number, just a rectangular form of a complex number. You see a plus ib. So we can use the square root of a squared plus b squared formula. Same with the bottom. This is a plus ib, where b is this whole thing. Okay, so I think that's what I'm gonna do. I'm really sorry, I'm very unsure of this. Okay. And what we can do is, because we know that, do you remember this? We can say that square root of a over square root of b is the same as square root of a over b. So what I'm gonna do is, I'm gonna combine this square root and this square root together, right? I'm gonna combine the square roots together. So this, I combine this together, and then we can square both sides of this equation, right? If you square both sides, you can drop away the square root. So I can drop away, sorry, I can drop away the square root and drop away the square root. I should be able to get this to, and then after dropping away the square root, you can multiply it to this side. Trying to make sure I don't make any mistakes, okay? Sorry. Then I'm gonna expand this. I'm gonna expand this like this, okay? You see this square? I'm gonna give it to this guy and give it to omega c1. Okay, you'll see why later. Yeah, okay, I'm gonna expand this. I'm also gonna do it on the other side. So see this? I'm gonna distribute this square to here and to here. I'm just using my creativity to work out this problem. I have no idea whether this is right or wrong. So you see, I take 2 minus 1, I'll get 1. Okay, 1 here. 2 minus 1, I'll get 1. Then the term, this, I keep it to this side, and this, I'm gonna bring it over to this side. Okay, so if I do that, okay, I'll get this, and then I put a minus sign here. What else can I do? Okay, see, the reason why I distribute the square, right, is so that I can factorize this out. Factorize this, and factorize this. So I'm gonna factorize that out, leaving behind this. Then the terms here, here, I copy it down. Right? Okay. Then remember our objective is to find omega. So I'm gonna bring this to the other side. R2 plus R3 square minus 2. Yeah. And then you're left with this. Then you can take square roots on both sides, this and this, to get rid of this square. Then okay, yeah, you're left with this square root of this denominator. And then this C, I just divide it over to this side, right? So you get C1 down here. Yeah. Okay. Wow, this is a a challenging question. I like it. Okay. So this is your cutoff frequency. Your cutoff frequency is this. I'm pretty sure it's correct because cutoff frequencies have a, you expect them to be 1 over C1 times R. Yeah, it's dimensionally consistent. So I think this is correct. Oh, that was not easy, but I like the challenge. So yes, that's it. Um, so that was a cutoff frequency. Is there any more questions? Is it really until C? Hold on, I need to check. Yeah. Oh, okay. There's also a skip here, amplitude plot question. So this is the cutoff frequency, and apparently there's a question D. Ah, wait, the question D is above the QR code. Okay, here. Ah, okay. So what does it mean by amplitude plot? Amplitude plot means bold, Bodhi plot or bold plot or whatever. I don't know. And it's been 2 semesters and I never know how to pronounce bold plot. Okay, anyways. So you need several things to draw the bold plot. Number one, the shape. Okay. The shape is whether it's a low pass or a high pass. In this case, it's a low pass filter. Why? Because going back for our low frequency limit and high frequency limit, we've identified that the low frequency limit is a higher value than the high frequency limit. Okay, so this is the higher value, therefore it's a low pass filter. So we know that the shape is generally like this. So it's something at low frequencies, something at low frequencies, nothing at high frequencies. I better draw that clearly. Okay, and this value is the decibel version of your H naught. Okay, so 20 log base 10 of the H naught. And our H naught we got earlier was what? I forgot. R2 over R1, is it? Yeah, R2 over R1. R2 over R1. They didn't give us any numerical values. So we'll just label here 20 log base 10 of R2 over R1. Okay. Then we have our cutoff frequency. So how to draw the cutoff frequency? First, drop by 3 decibels. Then you draw a horizontal line across. Then you drop down from here. This corresponding frequency is your cutoff frequency. And your cutoff frequency is this ginormous thing. Let me see if I can copy it without rewriting it. Yeah, baby. Okay, so yeah, this is your cutoff frequency. Yeah, so this omega C is your cutoff frequency. And the low pass filter, you have your maximum gain, the drop off at 3 dB. Oh yeah, and I forgot to label this as minus 20 dB per decade. And this is your omega axis. If you want to know, this is your decibel version of your gain. Okay, that's it. That's all the questions of this paper. It took me a whole day to record this. I have no idea why. By the time I was finishing question 3 just now, I was super tired. I was hungry. I felt like I was going to take a shower. And after that, I went to dinner and I did take a shower. And on my way back from dinner, I saw some of my friends. Yeah, they're gonna take this paper. I mean, 2009 paper tomorrow. So good luck to them, and good luck to you all too, because tomorrow's the finals. And by the way, uh, so I just started my Ko-Fi account. So this QR code is for my this Ko-Fi. I think it's coffee. Yeah. Anyways, so this QR will lead you to my coffee page. Basically, coffee is a donation page where you can donate uh any amount you want. So I set it to like $5 per pack of donation. Yeah. So I hope y'all can support me because peer tutoring is actually an unpaid job, FYI. And even a further FYI is that other schools pay their peer tutors, whereas MAE doesn't. I have no idea. I don't question these things. Anyways, I feel the experience was already fulfilling enough. So if I want to search for any reward or incentive, I guess I have that to cope. But it really does help if you can donate to the channel so that I can grow. So like, for example, things that I can grow in, I can create more content at a larger quantity. So we have more courses. I get a lot of students asking me for more courses other than just 2009. So there's that. And maybe more 2009 itself, but I think people are quite sick of it. So I can explore other other mods other than just electrical circuits. And other than that, something I really wanted to improve in this channel is the overall quality. So what do I mean by quality? For example, the recording quality, the technologies I use to do these videos. For example, the software that I'm using right now to record these videos is just the Teams recording. My God, it got me so many technical errors. So if I can get a video recording software, then that'll be great to enhance the quality. And when I look back in my past videos, the sound quality, like sometimes you can hear if nobody is talking, you can hear white noise, and I find that a bit irritating. Yeah, so my vision is to make this channel not just a learning palette, but also to make the process of learning enjoyable. Maybe to the extent of like a luxury kind of feeling, There's something I envision about my channel. Because, you know, the psychology and comfort of your learning process really adds to the whole experience overall. Like one of the feedback I got from my peer tutoring as a whole was that the guy like really because of the peer tutoring, he looked forward. I'm gonna use this word. He looked forward to tutorials and the finals. Well, that was a really unique feedback that I got. So yeah, I just want to enhance the quality. So it's not much of a watching these videos to survive, but really watching these videos to actually enjoy the process of learning. So it will really help if we can enhance the quality and enhance how viewers receive this the content of the channel. Yeah. And moreover, I over the semester and I think over future semesters, I'm probably gonna be working part-time as well. So if we can get more donations, it can free up my burden from doing those part-time work and help me devote my commitment into this channel to grow this channel. So that's really how it can help us grow. Yeah. And I know most of the students who are taking 2009 are year two students. So you got what, year three, year four to do. Personally, the mods that I've taken are the year three mods that I've taken are control theory, fluid mechanics, solid mechanics. Yeah. So yeah, if you can really help me make more time to grow this channel, I can help speed up and get more content out for your semester if you're taking the year three courses. So yeah, please help me. And if you decide not to donate to me on Coffee or Ko-fi, I don't know, you can help me spread the word. So thank you. And on that note, good luck for your final paper tomorrow because I know people are gonna have their 2022 23 sem 2 paper tomorrow. So good luck. You've been with me since my very first videos, and I've been doing peer tutoring for like 2 semesters already. So man, it's been a tiring journey, and I can't believe I'm still doing it in the semester that I'm technically not doing peer tutoring. And it's I don't know because people's support it just really ignites my passion into making these videos. So yeah, I'm really grateful that I have your support. So it means a lot to me. Thank you.